Hi there, this is an Algebra 1 video. It is Chapter 7, Section 8, and today we are learning about recursive formulas. This is the last section in the chapter, so you know that a test is coming your way very, very soon. And before we get started with the example at hand, I just want to define for you, if you will, the difference between a recursive formula and what you've seen up until now, which is an explicit formula. Explicit formulas are like the things that you've been graphing, like y equals mx plus b, for example. Something that says y equals 2x plus 3 would be an example of an explicit formula. And an explicit formula allows you to find any term of a sequence by using a variable. For example, you can have, well, let's not go there. I don't want to confuse you too much. But basically, you can find the value given the value of x. A recursive formula is unique or different in that a recursive formula is something that is repeating itself, so to speak. So in a recursive formula, you have to have the preceding term in order to figure out what the next term is. And so you can find the nth term of a sequence by performing operations to one or more of the preceding terms. So in this case, for example, in example 1 here, it says find the first 5 terms of the sequence in which a sub 1 equals 7. So see, they had to have told me what the previous term was in order for me to figure out what the next term is. That's not necessarily the case when you have an explicit formula. And later on in the lesson, we'll be talking about explicit formulas a bit more in depth. So in this case, how do I find the first 5 terms of the sequence? Where a sub 1 equals 7, and the formula is given here, a sub n equals 3 times a sub n minus 1 minus 12. And of course, this part is actually pretty important. I don't want you to just ignore the n greater than or equal to 2 here. That, my dears, is important because it gives you the domain of the formula. And basically, if n was not greater than or equal to 2, then this wouldn't make any sense, because the a sub n minus 1 just really means the n value minus 1. So if this n value is 2, equal to 2, then you would get 2 minus 1, which would be 1, and that would be the first term. If, for example, we allowed n to be something smaller than 2, like 1, for example, then it would be 1 minus 1 equals 0, and you'd have a sub 0, which would not even exist because the first term is a sub 1, so a sub 0 is like before the first, which doesn't make any sense for a recursive formula. So it's important that we put the n greater than or equal to 2. So how do we do this? Very simply, we want to find a sub 2. I'm going to go ahead and, because we already know that the first term is 7, a sub 1, so we now want to find a sub 2. So in our formula, we're going to put 3 a sub 2 minus 1. So we're going to replace the little n variable with a 2. And so that's going to be then minus 12. And that's going to be 3 times a sub 2 minus 1 is 1. And since we already know that a sub 1 is 7, we're going to go 3 times 7 minus 12. And 3 times 7 is 21. And 21 minus 12 is going to give us 9. So a sub 2 equals 9. And that's pretty much how you do this. And basically what we have to do is do this a few more times. They want the first 5 terms of the sequence. Now lucky for us, we already know the first one. The first one is 7. So I'm going to go ahead and put my answers up here. We know that the first term is 7. The second term is 9. So we basically have to do this 3 more times to get the next 3. So let's continue. We want now a sub 3. That's going to be 3 times a sub 3 minus 1 minus 12. So you see how each time 3 minus 1 is now going to give us 2. And we already know what a sub 2 is because we figured it out previously. So it's always based on the previous answer. So we're going to get 3 times a sub 2, which was 9, minus 12, which is then 27 minus 12. And 27 minus 12 is 15. So now we have our third term, which is 15. So now we're going to find a sub 4. And of course, a sub 4 is going to be 3 times a sub 4 minus 1 minus 12, which is going to be 3 times a sub 3 minus 12. And a sub 3 we found from here. Didn't write it down there, but a sub 3 is 15. So 3 times 15 minus 12. 3 times 15 is 45. And 45 minus 12 is 33. So now we're going to add 33. And so far we have the first 4 terms. And then lastly, we're going to do a sub 5. We're going to squeeze it in here. And that's going to be 3 times a sub 5 minus 1 minus 12. Okay, so that's going to equal 3 times a sub 5 minus 1 is 4. And again, a sub 4 was 33. So that's going to give us 99 minus 12. And then a sub 5 is going to be 87. And so we'll put our last term up there as 87. So now we have the first 5 terms of the sequence, which are 7, 9, 15, 33, and 87. So now I would like for you to do this do-it-yourself question, and then we will move on to writing recursive formulas. And before we do that, I would like to remind you of the 2 types of recursive formulas that we've dealt with thus far in Algebra 1. The first is an arithmetic sequence. And hopefully you recall that with an arithmetic sequence, there's always a common difference, and we call that common difference D. And you can find the common difference by subtracting a term from its preceding term, and if that number is constant throughout the sequence, then we call that the common difference. The formula for an arithmetic sequence is right here, a sub n equals a sub n minus 1 plus the common difference, which is D. But also in this chapter, we learned about geometric sequences. And in a geometric sequence, you don't have a common difference, you have a common ratio, which we use the letter R to represent. And the common ratio can be found similar to the common difference in that you have to use the previous term, but this time you're looking for division. You take a term and divide it by the previous term, and if you have that same ratio throughout, we call that the common ratio. And the formula for a geometric sequence is a sub n equals that common ratio times a sub n minus 1. Alrighty, so that being said, we're going to use that information for this example. It says write a recursive formula for each sequence. Now the first thing we have to do in this scenario is to determine whether or not we're dealing with an arithmetic sequence or a geometric sequence. So I'm going to go ahead and start by subtracting. So we know that 17 or 13 minus 17 is negative 4. 9 minus 13 is also negative 4. And 5 minus 9 is also negative 4. So in this case, we have a common difference, which is negative 4. Now we could try the common ratio, but we know that it's not going to work because it already worked with the common difference. So over here, I'm going to assume that it's a common ratio because I don't think they would give me 2 of the same kind in the same problem. But who knows? If it didn't work, we can always try the common difference after. But I'm going to try the common ratio. And 24 divided by 6 is 4. And 96 divided by 24 is also 4. And 384 divided by 96 is also 4. So here we actually have a common ratio of positive 4. Okay? And so now that we know which type of sequence it is, then we can actually use the appropriate formula. So for an arithmetic sequence where you have a common difference, we're going to get a sub n is equal to a sub n minus 1, here's our variable, and then we add the common difference, so plus negative 4 or just minus 4. This would be our recursive formula for part A. And of course, we would have to make sure that we say that a sub 1, you always want to list the first term, a sub 1 is 17, and of course that n is greater than or equal to 2. You don't want to forget those parts. Alrighty, and now for the other one, we have that it was a geometric sequence. So in that case, we're going to get a sub n is equal to 4 times a sub n minus 1. So we take 4, which is the common ratio, and times it by a sub n minus 1. But again, you want to make sure that you list the first term. So we want to say that a sub 1 is equal to 6, because that's the first term in this case. And you also want to say that n has to be greater than or equal to 2. And that is how you write a recursive formula from a given sequence. So now you will try with this do-it-yourself example. And then we will go on to do this for a word problem. I don't know how much you love word problems. All right, so this word problem is actually asking us to refer to the beginning of the lesson, but I went ahead and wrote it out for you. It says, clients of a shuttle service get picked up from their homes and driven to premium outlet stores for shopping. How nice of them. The total cost of the service depends on the total number of customers. The costs for the first 6 customers are shown. We have a T-table over there for you. So let n be the number of customers. They want us to A, write a recursive formula for the sequence, and then in part B, they want us to write an explicit formula. So we talked about that a little earlier, about the difference between a recursive and an explicit. So now you can see how we can get both from the information at hand. Alrighty, so we want to start with part A and kind of figure out whether or not it's going to be a geometric or a arithmetic sequence. So we do that by coming over here and realizing that if I go 35 minus 25, I get 10. 45 minus 35 is 10. 55 minus 45 is 10. 65 minus 55 is 10. And of course, 75 minus 65 is 10. So it turns out that all of these values have a common difference of 10. So that tells me that D is 10. And according to my formula, it's going to be a sub n is equal to a sub n minus 1 plus the common difference, which in this case happens to be 10. That's my first part. But now I can actually go ahead and give the other information as well. Remember, we have to always say a sub 1 would be the first term. That would be one customer. A sub 1 is 25. And of course, that n has to be greater than or equal to 2. So that pretty much in a nutshell is part A for you. But now we want to take this and actually write an explicit formula. And an explicit formula is one that doesn't have the n minus 1 thing. The n minus 1 is basically what tells us to go to the preceding term. And we don't want to have to go to the preceding term. So in an explicit formula, we have to figure out what that is. So we had a formula from a previous chapter. I don't know if you remember it or not, but it was basically here. A sub n is equal to a sub 1 plus n minus 1 times the common difference. This is the formula that we used in the previous chapter, so hopefully you still remember it. But we can use this formula to find the explicit form of this formula for the sequence. So in this case, we know what a sub 1 is. We know that a sub 1 is 25. So we plug in 25 for a sub 1, and we know that the common difference in this case is 10. So we replace D with 10. And now it's just a matter of some algebra, and then we can get our answers. So I'm going to go ahead and bring my work over here. So we have equals 25 plus, and we want to distribute 10 times n, which is 10n, and 10 times -1, which is -10. We then want to combine our like terms, 25 minus 10, which will give us 15. So we have 10n plus 15, and that is basically our explicit formula. Notice how the explicit formula doesn't involve any of the n minus 1 stuff. All right, so 10n plus 15 is our explicit formula. So now I'd like for you to try this word problem. It gives you the values here. This is the first term, second term, third term, fourth term. You have 4 terms to work with. And again, you want to have a recursive formula and an explicit formula for this sequence. And then we're going to be doing much the same thing, only instead of a word problem, we just have a direct question here. It says, write a recursive formula for a sub n equals 6n plus 3. So how do we do that? Well, we know from this that the common difference is going to be 6, because even if you look at the previous problem, let me go back here, the d times the n, that was the common difference, like the 10n, so we had 10n. So 10 is the common difference, right? So in the same way, for our problem at hand, we know that because there's a 6 in front of the n, that the common difference here is 6. And then we could figure out what a sub 1 was, because you have to have that as well. A sub 1 would equal 6 times 1 plus 3. So we would replace the n with a 1, and you would get 6 times 1 plus 3, which would basically equal 6 plus 3, or just 9. So a sub 1 equals 9, and that's all we need for our formula. So our formula would be a sub 1 equals 9, and then a sub n is equal to a sub n minus 1 plus the common difference, which is 6. And of course, we state that n has to be greater than or equal to 2. So this would be our recursive formula for part A. All right. Then in part B, we're doing exactly basically what we did in the previous example with the word problem, and that is to have or to write an explicit formula for this little guy. Alrighty, so we know that this is going to be a geometric sequence because we have the multiplication here going on instead of the addition that happens with the arithmetic sequence. This is a geometric sequence, and the common ratio is 0.8. The first term is 120. So we're going to go ahead and say a sub n is equal to, if you remember, we're going to put the first term, which is 120, and then it's going to be times the common ratio, which is 0.8, and then to the n minus 1 power. This is the formula that we just did in this chapter. So basically you have the initial amount, the first term goes here. So I can actually write it out for you. I'll put it here, a sub n is equal to a sub 1 times r to the n minus 1 power. Okay, that's the formula that we use. And so basically all I did is I took the a sub 1, which we know is 120, and plugged it in. We know the common ratio is 0.8, so I plugged that in, and then the exponent is just n minus 1. So this is our explicit formula for part B, 120 times 0.8 to the n minus 1 power. So now you can try this last do-it-yourself question, and once you've completed this do-it-yourself question, you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.